So hello and welcome to today's webinar, Sample Size and Prediction Calculation Interactions, a webinar going over sample size determination and prediction calculations, particularly in the context of clinical trials, and looking at some of the areas of overlap and interesting synergy between these two distinct philosophies and areas and calculations in the context of clinical trials. The two case studies we'll be focusing on today is milestone prediction in the context of group sequential design and sample size determination for clinical prediction models. Before we get started, just a few frequently asked questions. Firstly, is this webinar being recorded? Yes, and the recording will be sent to you after this webinar is complete. If you have any questions, please feel free to enter them into the questions tab on the right-hand side of your webinar software, and I'll try to answer as many of those as possible at the end, but most likely I will answer those via email for any that I don't actually get to. The slides will also be sent with the webinar recording later today. All right, so as mentioned, today's webinar, Sample Size and Prediction Calculations Interactions, we'll be looking at the interactions between these two areas of sample size determination and prediction calculations, and today's webinar is demonstrated on Encri, who sponsored today's webinar. Before we get started, let me introduce myself. My name is Ronan Fitzpatrick. I'm the head of statistics here at Encri, and I've been the Encri lead researcher since Encri Interim 3.0. I've given workshops at places like the FDA, JSM, hopefully in the near future, getting back out there on the road again, but obviously doing a lot of these webinars and similar for both internally here and obviously with other organizations as well. So what are we covering today? Firstly, we'll just have a brief introduction to both sample size determination and prediction calculations, just to kind of give a little bit of context, but not a huge focus today, and then focusing on the two case studies where the areas of sample size determination and prediction calculations interact quite strongly, namely the prediction of milestones, such as when our interim analysis is going to happen in group sequential design, and then sample size determination for clinical prediction models. And then there'll be a brief moment of conclusions and discussion at the end of the webinar, including some of the questions being answered if we have time. As mentioned, this webinar is presented by Encri. Encri is the complete solution for optimizing your clinical trial from early phase up to confirmatory designs. It covers a wide variety of fixed term, Bayesian, and adaptive designs, and is used by over 90% of organizations who had trials approved by the FDA have a license of Encri. You can see some of the reviews here. So with that out of the way, let's just get into the very brief introduction to both sample size determination and prediction to kind of just make sure that everyone's on the same page. So sample size and prediction. Well, sample size determination, of course, we know quite well from these Encri webinars, is focused on finding the appropriate sample size for your study. And usually this is based on some type of statistical goal or success criterion, and this is usually mostly done on a pre-trial basis. Now, of course, adaptive design kind of moves us a little beyond this, but the primary focus is how many people do I need in my study to be able to say that I have a high chance of success. And success might be defined such as statistical power, which is obviously your probability of rejecting the null hypothesis when the null hypothesis is false. The interval width, if you're looking at a confidence interval, is your kind of primary goal. And then there's other things like interim stopping rules in the context of group sequential design, which is what we'll talk about later on. On the other hand, prediction is usually focused on projecting future outcomes in our trials. So we're interested in kind of more practical outcomes, such as like when is X going to happen, how likely is X going to happen, and this is usually based on models which either use pre-existing data, either from other trials or other data sources, databases, etc., or perhaps more interestingly, based on the interim data that has become available in your trial as it's ongoing. So from a sample size perspective, usually the data as it come in is really only being used to define what's going to happen based on some pre-specified rules. Whereas in the prediction area, because we're not making the statistical inference, typically we're kind of just talking about practical things like like enrollment goals and stuff like that, then we have more flexibility to kind of just use the interim data fully and exercise that and kind of make dynamic choices based on that. And so you have things like milestone prediction, like reaching events or enrollment goals, clinical prediction tools, success failure probabilities, stuff like this. And these are kind of where prediction is usually used. So while sample size is usually focused on these kind of pre-trial statistical success criteria, prediction is usually focused on these more practical success criteria in inverted commas. So this idea of like, power is very tied in with the inference framework that you chose to use for your clinical trial, whereas prediction is focused on practical things like, well, how long is it actually going to take me to get to the point where I can decide to make a statistical choice or not based on the information that's become available. And that's where these interaction areas can kind of become quite interesting, because sample size is kind of more trended towards the statistical side and based on the kind of more pre-trial assumptions, whereas these prediction things is more towards practical kind of real world considerations and on a more ongoing basis. So the two interaction areas we're going to talk about today, as I mentioned earlier, are the milestone prediction for group sequential design and sample size determination for clinical prediction model criteria. So we'll get straight into the first case study, clinical trial milestone prediction. So there's kind of two main milestones that we're going to talk about today: enrollment prediction, which is mostly relevant for pretty much any clinical trial that you're in, and then event prediction, which is more specialized towards survival or time to event trials. So let's briefly talk about enrollment prediction first, albeit our case study will focus on the more complex problem of event prediction. So enrollment prediction, it's pretty simple. Basically, you have a clinical trial. You've probably done a sample size calculation. So you're now going, okay, we need 1,000 people in our study to be able to make the inferences that we want. But now we have the problem that we need to, find sites, open sites, recruit people, and before you even recruit them, once you recruit them, you need to screen them. You need to assign them to your respective treatment groups. And there's a whole pipeline that's required to get, from the abstract concept of a sample up to actual people in your study being assigned your treatment or not. And that's where enrollment prediction comes in. It's kind of taking that pipeline and turning that into a statistical model that can be used to then generate reasonable predictions of what you think is going to happen, usually based on what's happened so far, or perhaps based on other similar studies which had similar enrollment plans. So these sample size milestones, these enrollment milestones, are a key milestone for the vast majority of clinical trials. And you can find statistics that the majority of trials fail to reach their enrollment goals. So this is obviously something that is very important to trialists on the ground. And the level that you want to treat as a statistical problem or as a kind of more logistical problem or logistical modeling, kind of say Markov type modeling, is really up to yourself. But for today's purpose, we'll kind of treat the the enrollment process as if it was just a statistical process and kind of ignoring the complications of screening and such. But even within that, we can't ignore the kind of practical realities of our trial completely. So there's kind of multiple levels that you could think of the enrollment process of coming from. You could think of it as a global process. So basically, you're recruiting 10 people per month. And basically you could go, okay, that's going to roughly give us what's going to happen in future months. Not too interested in how those are distributed across our sites. We're just going to model as if it was a global process. But if we wanted to go down to another layer, we could look at regions. So some regions might be doing better than others, like states or countries and EU. And then, one level below that would simply be modeling individual sites, for example, hospitals, and then seeing how they're doing and then recruiting or removing hospitals based on their performance thus far. Like these key decisions that people are making are kind of on are trying to make the best decision possible to ensure that they reach their goal, which is getting enough people into the trial so that they can actually do the analysis that the trial is designed to do. So I'd say adding and dropping sites makes sense. And like, if you're talking about then, well, how do we do this modeling just from a kind of simplified context where we're just kind of treating this as a statistical process rather than a kind of logistical process, then there's a variety of different ways you could, like, there's fairly simple equations that you could use, there's simulation, there's kind of Bayesian approaches if you want to borrow from previous studies, and all of these are probably based around one statistical model or another, such as like gamma Poisson or piecewise Poisson or similar. And so that's one type of goal, and that's one that's very relevant for pretty much any trial. On the other hand, if we're talking about survival trials or time to event trials, then the key thing that's of interest at that point is our events. So the actual happening of the event of interest, whether that be progression in the context of an oncology trial, whether that be, a death, which obviously is something that means you're not going to be in the overall survival cohort. And so we're usually worried about using inference, using Cox regression or log rank tests about how long it takes for that event to occur. And of course, we're trying to see whether the time that it takes on your treatment group is less than the time on the control group, assuming that the event is a negative, which usually is, such as death. So yeah, overall survival, progression-free survival, these are common endpoints. But the important thing in the context of survival trials is that the statistical decisions, is particularly when to end a trial and do the right censoring, or when to do an interim analysis, these are based on the event process, not the enrollment process. So really, if you have 1,000 people but no one's had the event, from a practical point of view in a survival trial, that cohort has not given you any fully usable information yet. Now, obviously, if everyone survived for like 12 months already, that's giving you some information, but from the inferential point of view of distinguishing between your two groups, you're not getting what you need to be actual to do the time to event comparison. So in a survival trial, similar to what I often say in the context of sample size determination for survival trials, it's the events that are driving the inference, not the sample size. The sample size is really just a meta process creating people who can have the event. So the big thing that means is that if you're doing a survival trial, that if we're doing modeling of when we want to do the interim analysis or when we think the trial is going to end, we need to model the event process explicitly, not just the enrollment process. We can't just focus on how recruitment is going. And because you now have this more complex situation where you need to model not only the survival process, but you'll probably need to model the enrollment process, particularly if the enrollment is still ongoing at the point that you're making this prediction. But you also need to model competing processes like dropout, cure fraction, things like this. Then you're in a situation where this is a much more comprehensive level of modeling required to kind of get an accurate inference about the when events are going to occur, when milestone like number of events is going to occur. And enrollment itself, as we mentioned, very often deviates from the assumed projection per pre-trial, while it's even more so true for survival trials, where the expectations up front can often be quite different from what actually happens in the trial. That's why we're doing, of course, to a certain extent, that's why we're doing trials, because we don't know what's going to happen. If we knew what's going to happen beforehand, we wouldn't need to do clinical trials. We could just approve drugs based on our, priors, or based on our, information that we thought was true, or our phase 2, phase 1 type trials. So this all makes sense. But if we're talking about enrollment prediction and survival prediction, if we're talking to other stakeholders, people involved in the trial, sponsors, and the trial's been ongoing for some time and it's behind schedule, it's really important at that point to understand, based on what, if we just stick with where we're doing, how long is this going to take, and then also what are the type of things we could do to get this thing back on track. That's where this prediction makes sense. And when we're talking about group sequential design, which I don't really talk about here today in any detail, but basically in a group sequential design, you have multiple pre-specified interim analyses. Say, for example, let's just say you have one interim analysis after 50% of the sample size, if you're talking about the means or proportions, or let's say 50% of the events occur, then in that case, we may want to, at that interim analysis, know when the study is going to end, or perhaps when we start the trial, we want to know not only when is the trial going to end, but when is the trial going to have its interim analyses. So today we're going to focus on that former scenario where we effectively have a group sequential design. We assume that we got to the first interim analysis, and now because we have the information, because we have to unblind it, because that's how group sequential design works, you have to do a comparative analysis, or more accurately, the data monitoring committee is likely to be doing that. Then it makes sense that, well, we already are doing this analysis, we already have access to this data. Perhaps it would make sense to use that data to get a more accurate projection of when this study is going to end, compared to where we thought it was going to end, using our pre-trial sample size determination. And so, just to briefly mention, there's a variety of different methods available for enrollment and event prediction, of course. These are in these slides here, but we'll be focusing on the simulation approach in today's webinar. So as I said, we're just going to take a kind of relatively simple group sequential design. We're going to take the scenario where we design this trial and then we get our goal for the interim analysis, which this is a survival trial, so that'll be based on the number of events. And then we're going to do some playing around with prediction type tools to see, well, based on that, how much deviation do we have from the initial assumptions? And then what kind of things would we perhaps do to try and get this trial back on track, like say increase the sample size, for example. So there's nothing too crazy here. We're talking about a trial where there's placebo median survival of 5 months, 7 months in the treatment group. We're talking about 0.225 at the one-sided test, very common for standard alpha level for a clinical trial for phase 3. So the initially expected accrual period is 24 months with a minimum follow-up of 30 months. So most of the study length will be recruitment will be ongoing. Only the last 6 months, the last half a year will the recruitment be finished. And then we can see that they expect dropout of around 4% per year, and they are going to have a sample size of 230, which we'll see quite quickly is actually gives us a power of around 90%. So chicken and egg kind of thing here. The way they described this, they talked about the sample size first, but I assume that this was derived from the power calculation. And then in terms of the group sequential design aspect, we're going to talk about a two-look design. So one interim analysis, one final analysis, and with the interim analysis happening halfway through the trial in terms of the event information. So very importantly, that's not when half the subjects are recruited, that's when half the target events have occurred. And of course, we haven't got the target events here yet, but we're going to do that calculation in a moment. And just in terms of the spending functions, both the efficacy and the futility bounds will be the Huang-Shi-Dicani gamma spending function with a -5 gamma value or HSD parameter. And just to say that the futility bounds would be non-binding as expected. Very rare in clinical trials that you would have a binding futility boundary. I think most sponsors like to have the flexibility that if they cross the futility boundary, that they aren't forced to stop the trial early without affecting the overall type 1 error, which is what happens if you have a binding futility bound. So I think the first thing you want to do then is just look at look at the is to do this sample size calculation in Enquiry, and then we'll have an idea of what the overall design looks like, what the number of events is, where the interim analyses are likely to occur based on that information. So what I'm using here is STT25. This is a sample size table which is for group sequential design for piecewise accrual and piecewise event rates and piecewise dropout. So if we wanted to do in this table, we can specify that the event rate changes over time or the dropout rate changes over time. But in this case, actually, it's just a constant event rate, constant dropout rate. So things are a little bit simpler. So we'll specify the things that are quite easy that we kind of have from before. So we saw there's a one-sided 0.025 significance level, and we're going to specify 2 periods for our table because we want to have one period where accrual happens and then one period for the post-accrual period. So from 0 to 24 for when accrual happens, assumed to be uniform in the original sample size calculation, and then the remaining 6 months where accrual does not occur. And we'll get our hazard ratio in a moment. We'll need to use the 2 median survivals that we had there a moment ago to use that fully. So we're going to convert these median survivals into exponential rates. This is what's used in Enquiry. And we'll also need to convert this 4% dropout rate into an exponential rate as well, since that's just the way Enquiry generally uses this information. But before we do that, let's just focus on the group sequential design. So as mentioned, there will be 2 looks in total. So just to be clear about that, one interim analysis and one final analysis, and by default this is equally spaced design, like equally spaced looks, and that's what we're going to have today. So once half the total events occurs, we're going to do an interim analysis, and then once the total events that we're targeting occurs, we're going to do our final analysis. But remember, the sample size could be in various states of completion. The enrollment process might be in various states of completion by the time we reach that particular event's threshold. And then we want to add our 2 spending functions, which as mentioned were both Huang-Shi-Dicani or the gamma family with parameters of -5 in each of them. As mentioned, it's a non-binding futility bound because that means you have the flexibility that if you cross the futility boundary and you choose to continue the trial for whatever reason, that your trial would not have inflated type 1 error by making that choice. Obviously, just that flexibility for very little cost makes a lot of sense, and that's why it's generally the standard way this is done. Okay, so as I mentioned, we need to get the hazard ratio, and to do that, we're going to go to the assistance menu, and we're going to select the survival parameter converter. And in this, we're now going to enter our 5 and 7 months to get our hazard ratio. So remember, in group 1, we have a median survival of 5 months. In the other one, we have 7 months, and we get something like this. But we can also do this the other way around. It's basically the same thing. Basically, it's just this is the 1 divided the reciprocal of this. And you can see that the exponential rate for the treatment group is around 0.099, or basically 0.1, and it's about 0.14 in the control group. So if we're talking about the exponential rate on this month's rate, like if we were to turn this into like a year scale or the week scale by say dividing by 12 for years or multiplying by 4 for weeks, these numbers would obviously change. So we're implicitly using the time unit by the choice of whatever time unit we put into this median survival row. So we'll take this other hazard ratio here of about 0.714, and we'll enter that into the original table. Okay, and then we open this side table here, and this looks quite similar to stuff that I've done in previous webinars for survival, like STT3. Basically, in the first row, we need to specify the end of the time periods that are of interest in column 2 and 3. So we want the end of the column 2 period to be 24 weeks. That's the end of our accrual period, and then the end of the study to be 30 months in. And the only difference really between these two rows will be that, or these two columns, I should say, is that this is going to equal 100 for accrual percentage in column 2 and then 0 in column 3. So all we're specifying here is that we want 100% of the total recruitment to have happened between 0 and 24 months on a uniform basis, which is what we saw in the original sample size determination table. And then we want no more recruitment after 24 months up to 30 months, which is when the study is going to end. That's where we're planning to right censor the study. So then we need to get our exponential hazard rate. So we can easily get that by going in here and taking the value here. So we're going to take the control rate of about 0.14, and we're going to enter that into the group 1 exponential hazard rate. And you can see here that we get back 0.099 as we have from this table. So you can see that we're getting the correct exponential hazard rate for this particular hazard ratio. And you can see here that you also get, given that the trial had been fully stocked from the beginning, you'd see that we'd have expect around a 3.6% survival rate after 24 months, and then about 1.5 after 30 months in the control group, and that's closer to 9 and 5% respectively in the other group. Now, the other thing is you have these two exponential dropout rates, which obviously are allowed to be piecewise again, but they're constant in this case, and they specified that the exponential dropout rate should correspond to a 4% dropout rate per annum. And you can easily do that calculation in the same survival parameter converter tool. So all we need to do is to specify our exponential rate on the month scale. So that means if we're talking about rates per year, we need to have 12 months be the time that we're going to do the dropout process at, and then it's like how many people survive the dropout process. So this is the survival proportion. Well, it's 0.96, right? So we're saying after 12 months, 96% of people would survive this dropout process. And that gives you an exponential parameter or exponential dropout rate of around 0.003, which is significantly lower than the 2 event rates. That's what we probably expect in most clinical trials. And we basically just need to enter this value into the relevant rows, these 4 rows. Okay, so now this table is fully complete. So if we complete the rest of this calculation, so we set this sample size ratio to 1, and then we enter our sample size in each group of 230, then we'll see that we get approximately 90% power for this design, and that the group 1 events is around 197, and then the group 2 events is around 177. So unsurprisingly, we're getting more events in the control group versus the treatment group, more deaths in the control group versus the treatment group effectively. And we can see here that it's basically 198 plus 177. So this doesn't equal exactly an integer, but it's pretty close. So if we go back to our original looks table, which we can do by just simply selecting this looks tab at the bottom, then you can see that this table on the right has now been filled with the group sequential information. And you can see here that the total number of events is effectively around 375, and they would expect that this interim analysis, based on the exponential rates given, would occur around 17.34 months into the study. And basically you could make a fairly quick calculation of how that would correspond to the sample size expected at that time as well. So if we take 17.341 and we divide that by 24, which is the total expected accrual length, then we see that that's around 72% of the total accrual period. So assuming uniform accrual, if we multiply our total sample size 460, so 230 multiplied by 2, then we would expect that at this interim analysis we would have reached around 332 people would have been recruited at this time. So what we're saying here is that, with a fairly simple calculation, just take the ratio of the expected calendar time divided by the expected total accrual time. Then we multiply that by our total sample size. Then we're basically getting back what the expected enrollment will have occurred at this 17.34 time effectively. You can also see these efficacy bands. These are on the Z scale. These are basically just the log hazard ratio divided by the square root of 1 over the events in each group. And you can see here that we have an upper efficacy band of around 2.9 at the interim analyses, and then minus 1.26 at the futility boundary. And then obviously these converge at the final analysis. You either have defined for futility or efficacy at the final analysis. You have to make a decision at the final analysis. And you can see here that on the alpha scale, on the p-value scale, if we're just using a standard log-rank analysis, we have you need to have a p-value of around less 0.002 defined for significance at this interim analysis, but it's very close to the original 0.025 at this final analysis. And I think that reflects what usually happens with group design. You're kind of usually conservative at the interim analysis so that the final analysis is relatively representative or close to what the fixed term analysis would have been. This kind of reduces the area of controversy, I would call it, where effectively if you get a p-value at the end and it's 0.023 and they're going, that should be significant, and you're like, well, no, we spent alpha, so it isn't. You kind of want to avoid those kind of controversies usually when dealing with trialists and people like that. And so that's the design that we've done. So we've kind of replicated the sample size calculation. So what we have here is basically a full sample size calculation. We have 90% power, but once we get to this interim analysis, we might have a number of, once the actual interim analysis actually happens, when we reach like 187 or 188 sample size, let's just say 187, then the big question is, well, look, this is what we thought was going to happen before the trial started. If we were to take the real data as it became available that we're going to use for our interim analysis regardless, we could now make better inferences about what we think the rest of the trial is going to do based on that information, and then make practical ideas about like how much are we going to overshoot or undershoot this original total study length we were targeting of 30 when we needed to get this like 374 or 375 sample size calculation. And for this example, we actually have access to that data. This is like data that's available that we have available. So we're going to take the real data that existed at this interim analysis, and we're going to use that to make some calculations about like what happened in the actual trial versus what actually happened, what we expected to happen pre-trial, and then maybe some of the things you might do to kind of ameliorate the issues that might have existed between those two. So to do that, we'll just move over to the predict tool that was added in our most recent update 9.0, available in the expert tier. And we're going to basically do the kind of simplest calculation to allow the easiest comparisons. So we're going to use the unblinded events. So we're we're going to know the group assignment in the original data set, and we're going to use that group assignment. We're going to assume that enrollment status is ongoing, because it was in this case. And we expect that, of course, in our original calculation. Like, remember, this time that we set interim analysis is well below the accrual period, so of course we would assume that the accrual is still ongoing at this interim analysis. And we're also going to assume we're going to use the subject data only. So I've talked in the last 3 webinars a lot about this tool and looked at site data, but for comparison's sake, it'll be easier to kind of use the subject data only level and then be able to kind of quickly compare what happened compared to what actually we thought was going to happen in the kind of design stage. So we're going to use the subject example data set. We're going to have a treatment ID equal to treatment here. And we basically did this as just columns in the data set that we have. So if we go to subject example, you can see we have country, site ID, arrival time. So when did you arrive in the study? How long have you been on the study? Either until now, or in the case that you had an event, until you had an event, or a dropout if you had a dropout. What treatment group you were in as well as the other one. And status here is just, were you either available at the current time when this data set was taken, so you had been recruited but you hadn't had the event. Had you had the event, which is indicated by 1, and then there's -1 would mean that you've been dropped out. And just to say that obviously the dropout process doesn't have to be dropout. This is just anything that means that you as a subject were no longer available to have the event. So I think the big thing to take away from this first set of information, this accrual options thing, so this is based on the real data. We've kind of used the data to generate this information here, is that the current sample size is 402. So this is what, as we'll see in the next screen, we've basically reached the interim analysis. We have 187 events, but the current sample size is 402, which is fairly substantially higher than the 332 that we were expecting. And there could be multiple reasons that happens, right? Like, that could be that the recruitment is going slower than expected. It could be that the event process is going slower than expected. It could be that the dropout process is higher than expected, because obviously if you're dropping out, that's kind of taking away the number of people who can have the event. And all this contributes effectively to a number of hypotheses. But using this tool, we can kind of delve down in and see which one is the most likely to be true. And the first hypothesis we'll explore is, well, is the enrollment process slower than expected? Where we're recruiting people slower than we were hoping to? And we can do that by just checking what the accrual rate is up to this point. So in this case, it's around 19.4 per month. Okay, and how does that compare to what we originally had? Well, we can very easily calculate that by considering the expected overall recruitment rate, which would simply just be equal to the total sample size divided by the expected length of time. So if we have 460 people that we were expecting at the end of the study, and we thought that that would take 24 months to recruit. So remember, our accrual period is 24 months. We're thinking it would take 24 months to recruit 460 people. If we divide 460 by 24, we should get 19 points. So our original recruitment rate that we were expecting was around 19.2, which is actually slightly lower than the achieved recruitment rate. So based on this, it seems that the reason that the trial has taken longer to reach the interim analyses, the target number of events for the interim analyses, is not because the recruitment rate was slower. That seems to be more or less on target. So we click next, and then we get into the event and dropout information. And obviously, very quickly, we see this is where the action is. So if we go back to our original design, what were the event rates we were expecting in each group? We were expecting exponential event rates of about 1.4 and 0.1 in the control and treatment groups respectively. If we go to our prediction engine, the best exponential assumptions it has, so this is the kind of best fitting exponential values for the treatment control group, is about 0.1085 and 0.0813, both of which are below what we were expecting, particularly that control rate. That control rate seems a fairly substantial amount lower than expected. So remember, 0.1085 and 0.0813 versus 0.14 and 0.1, which is what we were expecting in the initial design stage. So the event process in both groups seems to be slower than expected. And we can also see that the hazard ratio here is slightly more conservative than what we were hoping for in the initial clinical trial. And I could certainly go through like sample size re-estimation and stuff if we're looking at like maybe that needs to change our sample size. But I think with this case, I think the power for that hazard ratio would still be, if targeted initially with this sample size, would have been around 85%. So it's not a huge difference. It's probably not a case where sample size re-estimation would be, probably necessary, though you may choose to have it if you wanted to. But focusing on the practical problem, which is, okay, we're not really worrying about the statistical inference side. We're kind of assuming that the power is still relatively high. It's not huge divergence. What we're really interested in here is like, okay, given that the event rate has turned out to be slower than expected, what is that practically going to mean for the length of the study, for how long it's going to take for us to get to the point where we finish this trial and reach the 374 events or 375 events we were targeting initially. And so it's important here that, like this is slightly less than expected, but the important thing for our perspective really is that the event rate is slower than expected. The target of events is 374, which is, you can make this 375 to correspond exactly to the original design. They're very close. Obviously, it depends kind of which algorithm you used, but it wouldn't make much of a difference in this case. And just to check, did dropout make much of a contribution to this? No, we can see that the dropout rate in both groups is both below 0.003. So the dropout rate is actually doing better than expected in the sense that there's less dropout than we initially planned for. Or were worried about. And that means that really what's driving the fact that this trial is taking longer than expected to reach the target that we expected initially to reach the end of the trial, where we're kind of behind schedule, is because of the event process. So remember, in this universe, we're about 20.7 months into this study. So we're obviously about 3 months behind where we hope to be in the initial study. So remember, we were initially targeting to have our interim analysis around 17.34 months into the study, and now we had to wait actually to 27.7 months. So about 3 extra months of time has passed over where we were hoping to do the interim analysis to reach the interim target number of events. So to reach the 187 events that we were initially looking for. So remember, we needed around 187 events. It's taken 3 months more than expected to get to that target and to do this interim analysis. So what are the implications if we assume that this trend will continue for the rest of the study on the actual end of the study time? Well, we can actually model that using the predict function. So if we just use the default assumptions, which are the best fitting assumptions, assuming a Poisson constant, like uniform accrual and exponential survival process, then we'll see very quickly that the total length of the study, based on the current trajectory, is a little bit behind where we were hoping it to be. So if we scroll over here to the results on the right, based on where we are right now, the accrual period is actually expected to finish a little bit earlier than expected, around 0.3 of a month. Maybe that's maybe a week and a half more like earlier than expected. But the total study length is like nearly 4 months longer than we expected. Now, whether that's such a considerable difference that you need to start considering some changes, getting more aggressive in recruitment, stuff like that, obviously it depends on the people on the ground and decisions they want to make. But based on what we know right now, we're expecting that this study will take around 4 months longer than expected. So that's that's a fairly, it's not a big deal, but I think in the context of clinical trials, many would probably take that because these kind of delays are almost routine. It's much rare to end up going on trial. There are cases where things go better than expected, like the COVID-19 vaccine trials in 2020 went better than expected, unfortunately, because COVID-19 was so prevalent. But in most clinical trials, it's the opposite problem that we're usually worried about. And we can see that even if we look at the kind of 95% range for the study duration, it's really between 32.3 and up to 35.7. So that's it's a range that's it's all above 30 by a significant amount. But so certainly it's hard to believe that based on how the trial is going right now, we're likely to end up getting where we wanted to be initially. And to be honest, if we go to the enrollment prediction plot, you can see that there was a little bit of a kind of slowing down in recent months, but we were using kind of the long-term trend. So if this slope decrease here was actually going forward, then we would actually need to be like more aggressive in terms of getting more sites back open and stuff like that. But we can see that the events prediction and stuff, this is kind of mostly fine. And then the dropout prediction is kind of why the dropout's relatively rare, so we're not getting much information there. And so the logical thing then to do is like, well, okay, if we play around with the kind of things that the degrees of freedom that we have, is there any way we could get this trial back on track? Could we do it like an ad hoc sample size increase? Because remember, they that's not without issues, and certainly you would have to go through the regulator and your DMC to do this, because you could potentially bias your trial, because if you're adding people to your trial, what that could mean is that if the event process is more aggressive in the initial stages, so that like the difference between the control and treatment group is more obvious in early stages of the disease, then you could be making your trial more optimistic than it actually is. Whereas if you were to choose to say increase the length of the time to wait for the 374, 375 to events to occur, you might be biasing more towards the latter end of the range. There's a very good paper by Friedland and Korn about sample size increases in the context of clinical survival trials and how this could potentially bias things. But for now, we'll assume that you have those degrees of freedom and that you're going to focus on perhaps increasing the sample size a little bit. And I've kind of pre-done a calculation here that would perhaps solve the problem. So let's assume that we're going to be more aggressive in recruitment going forward. We're going to open up a bunch of new sites, get people on board very quickly. We can have these in reserve, and assume the recruitment rate for the final, well, effectively in this case 4 months or something, we're going to increase that by about 50% over the original 20 per month that we had initially. And then we're going to increase the target sample size from 460 to 540. So we're going to increase that sample size requirement by about 80 basically. So remember, our initial target sample size from the calculation was 460. We're now jumping this up a bit to kind of reflect what we want. We're going to assume that this event process, we can't really change the event process, since that's the entire point of the trial, is to understand this and to get an accurate inference about this. So we're using degrees of freedom that we potentially could have, which is increasing the sample size, being more aggressive in recruitment, and we're seeing if that could potentially get our trial back on track. And obviously this is a pre-done calculation. We could go through a lot of scenarios, see how they each do, but for this particular scenario, if we were to do this kind of very aggressive plan and get that approved by the regulator, because they see perhaps they believe that the event rate or the difference between the two groups is constant over time, which is consistent with the exponential assumption, then in that case it's not as problematic to do something like this from a statistical inference point of view. And you can see here that if we did this, then we would end up getting a total study length that ends up being more representative of what we had initially. So it ends up being around 29.97, and the accrual duration only had to be increased by about 1.5 months to achieve that. So we've recruited 80 extra people, obviously not a trivial matter. We've had to be more aggressive to get more people into the trial quicker. Obviously that's incredibly untrivial, and it very much depends on the context of your trial, but if you were able to do that, then you could have got this trial back on track effectively. Or at least you would expect it to be back on track, and now you have a plan of action for what you're going to do going forward. And so hopefully that gives you an idea of where group sequential design and prediction can interact. So if you want to know the details of the prediction that I did there, you can see this on this slide here. But obviously I kind of inferred most of it from the original group sequential design and just kind of rounded some stuff up, like the sample size calculation was 375. This was actually 374 using the method that they use. I think they rounded their events instead of using the decimal values, and that's how you get the slight differences here. But in practical sense, they're more or less the same. And if we had more time, we can go over the effect of sites and blinded versus unblinded, but I've covered that a lot more in previous webinars. So if you're interested, feel free to go to, there's a link at the end of these slides where you can find all previous webinars, and I talk a lot more in this example from a prediction point of view outside of context group design in that webinar. So for our next section, we're going to look at sample size for prediction models. So we're going to look specifically at, we're talking about here is clinical prediction models, because clinical prediction models are basically these models are developed usually using demographic or other biomarker type data to create models that can help you make better risk evaluations, better probability assessments of likely diagnostic or prognostic purposes. So diagnostic obviously means like we're trying to find out if you have the disease or not. So using all these characteristics, can we predict or give a probability that you have the disease? But prognostic is, given these risk factors or other considerations, how likely is it that you're going to get the disease in the future? Like how likely you're going to have something happen to you going forward. So, more or less they're kind of doing similar things, but obviously they can have quite different considerations. And obviously in one case in diagnostic, you can get that information quite quickly because you could use a gold standard test and find out whether they actually do have the disease or not. Whereas for prognostic, you'll need to follow up a cohort for a period of time and actually find out how well the model did on people after follow up, and kind of use that to infer like whether the prognosis, the prognostic predictions were actually accurate or not. And the important thing with these models is that you don't just want a model that has kind of high performance metrics like R squared and stuff like that. You want it to also have good discrimination and good calibration. So discrimination is basically the ability of the model to put disease people higher than non-disease people, assuming that like higher means more likely to have the disease on whatever the scale of interest is, whether that be a probability or some kind of risk score. So that's discrimination. We want to basically be able to distinguish the two groups from each other, or the multiple groups from each other, that are of interest for our diagnostic or prognostic purposes. But calibration is also very important because we want to see that how representative were the outputs, or particularly the probability outputs of our model, to what actually happened. So you could have a model that's good at discrimination that always puts the disease people higher than the other people, but in terms of the probability it gave that you actually have the disease is a fair way off. And that's obviously more problematic when you apply that onto the population level, and you're maybe assigning more people to the disease group than there should be, and that's where you want calibration to be well. And calibration is probably the most difficult part of developing a prediction model. Like, I think anyone can put in data and get an R squared out. I think most people can understand like here's what the scores on average were for disease people versus non-disease people. Were they higher for disease people? Great, that's got decent discrimination. Or like you could do like a 2x2 table. Whereas calibration, you need to kind of map on the kind of statistical like the statistical model, the probabilities onto what actually happened, and then see whether that was accurate at the kind of at its best, at its most fundamental level, at the kind of lowest level of prediction or output available from the model. And prediction models have had a lot of success. So the Wells score, Q-risk, Nottingham prognostic score, these are widely used and they're growing ever more popular. Every day there are more and more papers preferring new prediction models for new disease types across any area that you can think of, from cardiology to psychology to social studies. Basically anywhere that prediction can happen, it's expected to happen. And obviously this kind of follows on from the huge success that we've seen for prediction as like predictive analytics, machine learning, areas such as that, in the context obviously of information technology, social media, areas like this, where these have been hugely successful in generating a lot of value, a lot of like shareholder and financial value in those areas. And inevitably there's a question of, well, if these are so good at creating these incredibly sophisticated prediction models in the context of ads and stuff like that, then why wouldn't we use this same type of approach for medical decision making? Why wouldn't we use all this data we have available in all these medical databases, from our various national authorities, and use this to make better predictions, better tools to quickly find out how much someone is at risk or how likely they actually have the disease, without having to do more invasive procedures, which gold standard tests often are. So we've seen this huge growth in the developments of these models, but it has been well noted for several years now that the quality of these models has not quite been where you would want it to be. So a lot of models are generated, but not much time has been spent on making sure these models actually stand up to scrutiny in real world clinical settings. And there's been a lot of work from a lot of great people on creating frameworks to hopefully create higher quality prediction models. So in particular, there's this tripod statement that was made, I think 3 or 4 years ago at this point, and they give a very good rundown of everything that you should put down, basically a checklist of I think 21 items that you should be able to specify and describe to basically like give you a good description of what your like how you're going to set up your study, who you're going to be using for your study, what are the success criteria for your study, how are you going to calibrate the use discrimination, how are you going to publish your results, are you going to make sure your results are all public, transparency. And it's just a situation where that's been designed to hopefully give a easy to use framework for people to quickly, well, not people to generate these models in a principled fashion, which means that the probability that a kind of erroneous clinical prediction model that looks better than expected is less likely to get through the gateway. So if we're talking about issues like that they focus on, they talk about selection bias, like the way that you like which subjects you pick or which ones you screen out or select has a huge effect on how representative that clinical prediction model might be in the real world. There's very little validation of the model, which is like where you see how well the model performs in out of sample problem. So basically you have 100, like you have 1,000 people, you develop your prediction models. Let's see how it does for 100 actual patients going forward in terms of say prognostic quality. Very little of that happens, very little validation, and very poor validation even when it does happen. The reporting of these models in terms of like being able to replicate them and into actually generating the model is very poor. And then there's just other kind of standard statistical problems and stuff like dichotomania, taking continuous measures, turning them into binary measures, like basically throwing away a lot of useful information that can be used for prediction. And when we're talking about prediction, we're talking about this more practical output. We're not really worried as much about the inferential statistics like the p-values and the confidence intervals. We're worried about, well, how well does this model discriminate disease people from non-disease people, or from people who are likely to get disease from people who are not likely to get disease, and how well do like the probabilities that come out of it for individual subjects correspond to how likely that person actually was to get the disease by taking the kind of the cohort of self-similar people, the subgroup, and seeing how they actually performed, like how many of them actually have the disease. And a very recent example was these COVID-19 prediction models, both prognostic and diagnostic. There was a review done by Wayland. 232 models were found. 226 of them were found to be at high risk of bias, and 0 of them were well validated. So there's a lot of work and papers generated on the creation of prediction models for COVID-19. The quality of that work is highly questionable based on this research and based on the study. So this is definitely happening still here. But one kind of low-hanging fruit of this area, like dealing with selection bias it's kind of complex. You need to think about epidemiology, think like confounding, collider bias, stuff like that. Validation requires you to have access to a whole suite of new information, new subjects to actually try your model on. Poor reporting is low-hanging fruit as well, and dichotomania is a poor hanging fruit. But some of these things take more effort to do. One simple thing that researchers could be doing to improve their ability to know whether their model is worth doing or worth trying based on the amount of information that I have is to do a formal sample size calculation. But unlike traditional sample size calculations, which are based on statistical criteria such as power and interval width, these are kind of inferential statistics. If we're talking about a prediction models, we're talking about these discrimination and calibration and model performance criteria, then we can just, they're still success criteria. We can still get reasonable ideas of how likely we are to get to a minimum level of these success criteria using, simulation, using sample size calculations, rather than using what's used right now, which is these ad hoc rules like 10 events per variable. So if you imagine a binary model and you either you're yes or no, disease, not disease, then you need 10 disease people per variable is the kind of rule of thumb, and that was found to be wholly inadequate for the actual purposes that the authors claimed that it should be used for. And that was a lot of good work done by people like Martin van Smeeden in terms of elucidating why that's so and doing sample size calculations that are more accurately like represent that. So there's people like Riley, Van Smeden, they've been really involved in generating a lot of sample size calculations that actually target the things you should be targeting if you want an effective prediction model. Now, to be clear, we're focusing here on prediction models that use kind of more, I suppose, traditional multivariable GLM regression type models. So linear, logistic, if you're talking about binary data, Cox, if we're talking about survival, like we're talking about here, your kind of standard tools that you're very familiar with statistics, but rather than using these for p-values and inference, although obviously you can still do that if you want to, we're focusing here on their performance in terms of them being able to output a probability of survival, a probability of being diseased, like a probability of getting a score, like a weight score, like their weight or something like that. Like how good is this model at making predictions about future samples based on the multi-variable model that we created using all of the variables that we know about age and gender and starting weight and socioeconomic factors, etc., etc. And these authors came up with 4 important criteria that should all be fulfilled if you want to have a good prediction model, or at least have a higher chance of having a good prediction model. And they thought these were the mean performance, which is basically just like how well does this do for the average person. So here's the average person, how well does this model do for them? And you can find relatively easy measures such as the margin of error, like your confidence intervals, to assess that. Individual performance is like an attempt to assess, well, how well does it do over the whole suite of individuals who are subjects, not just how well it does for the average person, but for the people who are like out on the extremes, who are more unusual, like you could even go into subgroup type stuff if you're going even further, but basically how well does it do over the entirety of it. And in this case we're looking at things like the absolute percentage error, or in the case of continuous data, the residual variance, just some measure of how well overall did the study do to fit each individual's in aggregate effectively. And obviously you could, in some cases, look at certain subgroups individually and see if certain subgroups hold up, particularly if those happen to be more important. But we're focusing here more on the macro level individual performance. And then there's 2 other concepts that we need to think about. We need to think about overfitting, and we think about the optimism adjustment effectively. So overfitting is basically just dealing with the fact that when we're talking about our model, which is done on the data we have available, inevitably there's going to be some overfitting to what's in that actual data set. So, our model will almost certainly work best on the data set that the model was built on compared to other data sets. Like, I think logically that makes sense. But you can use shrinkage or penalization to effectively, like there's various ways you can do this in terms of like removing variables and stuff like that. But basically, just you can if you know that a priori, you can apply an appropriate factor of shrinkage, kind of bring this back towards kind of mean values, kind of not get too much pulled out by kind of like outliers and stuff like that, and create a model which is more likely to represent the kind of better average performance in out of sample, in validation samples, for example, or in the actual real world. And so, this is something like overfitting is highly common, it's highly problematic, and therefore you can at least make some attempt to deal with the effect of overfitting, dealing with your kind of optimism as well, by basically making adjustments a priori for your model, rather than just kind of playing it by ear and saying, well, this model, like, it's overfitted, it's a bit optimistic, it's fine, we'll just kind of deal with that. You can actually deal with that and consider that at the sample size and the planning stage of your development of the prediction model. And you can do that using the optimism adjusted or squared. And there's also methods proposed for sample size for updating your model, like what sample size you need to update your model once you have new data available, like the external validation of the model, like how many people do I need my external validation set, my out of sample set, to validate my model. And there's way more work going on in this area. It's a very active area of research, very interesting. So if you're interested, certainly look into that. And just to say here on the right, there's these equations are for the kind of 4 criteria for the logistic or binary model for the margin of error, the mean absolute percentage error. This equation is kind of just taken from a simulation study to kind of get this. The overfitting sample size requirement. You can see this R squared here. This is kind of your Cox-Snell R squared. And then you have your optimism adjusted shrinkage, which basically is just inserted into this equation to get the N required for your optimism adjustment. So I'm going to take a very brief example here of calculating sample size from one of the kind of foundational papers in this area from Riley. And they basically took another paper by Huda where they developed a prediction model for to basically predicting fat-free mass. And they had a variety of they had a target R squared or adjusted R squared of 90%, and they expected a mean around 26.7 kilograms and 8.7 standard deviation. And you can see that for their model, they hope to have 20 predictors to accurately predict what your outcome was going to be on this scale of fat-free mass in children from 4 to 15. And they saw that for this case, you would need 254 people to develop a model that they feel would be likely to be able, useful for making predictions in this domain. So in terms of how this works in Encre, there's not really much to go on here because effectively this is a very simple Encre table. So if we go to Encre and we go to the compute minimum sample size here, or T15. So just to note, this isn't available in Encre right now. This will be included in our 9.1 update, which we're expecting to be released at the end of November. So this isn't available in the software right now. That's the disclaimer, but it's going to be available in approximately a month. This is a preview build. But obviously just to kind of get you interested in what we'll be doing in our next update, which will be focusing on mostly standard Encre tables opposed to 9.0, our recent update, which focused on the predict module, which we used here previously. So because this is relatively simple, we'll kind of quickly go through it. So we need our adjusted R squared. So this isn't the raw R squared that we expect from the model. This is an adjusted R squared, and we can kind of see what that means here on the right-hand side. So the adjusted R squared of the Cox-Snell R squared, which for the case of the linear case is really just the normal R squared. It's just the percentage of the variation explained by the model. So in this case, we're just using the adjusted R squared. We have 20 candidate parameters. So just to mention here that we're using approaches that might remove some of these parameters if they happen to be not very useful for making our assessment. We have our target length level of shrinkage, which is 0.9. We have our model intercept, which is equivalent to the mean value in this case, and that's equal to 26.7. So the intercept and the mean are basically the same thing in this case, with a standard deviation of 8.7. And then you can see that we need this multiplicative margin of error. This is set to 1.1. This is just kind of a common default suggested by the initial authors. So you can see the definition here. It's the maximum multiplicative margin of error used in the estimation of the intercept and residual standard deviation. So 1.1 or 10% would be the most commonly used value for this. You can see here the target level of shrinkage is used to adjust predictor effects to account for overfitting. So you can see here that we end up getting 254, which is what we saw from the original paper, and you can see that the 4 criteria that we used are explained here as they were in my slides. Like here's the 4 criteria, and we're basically taking the maximum sample size from these 4 calculations. So if we very quickly go back to our slide, go back a slide here. There's 4 equations. These are for logistic, but they're quite similar for linear regression. We have 4 criteria. We're going to do all 4 of these sample size calculations, and the one which has the maximum sample size is the one that we end up actually using for our purposes. In this case, I believe it's the 4th criteria, the optimism adjusted sample size. I think the shrinkage one actually ends up with the same sample size as well. And you can see here that's around 12.7, around 13 people per predictor, which you could see is a little bit above the kind of 10 per predictor kind of rule used kind of traditionally, albeit that's for logistic regression, but I assume it's kind of similar for linear, or kind of people have kind of transposed that to other models erroneously. You can see that the actual level of shrinkage is a little bit higher than the target level of shrinkage, but not disastrously so. And you can see that the mean, like the confidence interval for the mean for the intercept / mean is around 26.58 to 26.82, a relatively tight margin of error, I would say there. So you would probably be happy with the performance here for a sample size of 254. And you can see here that we get a full output kind of summary statement of what happened here as well. And in Enquiry, there will also be similar tools for the case of binary outcomes with logistic regression. Slightly different inputs here, but the principles are more or less the same. And then for the survival Cox regression model as well, similar ideas going on here. Now, each one obviously has its own distinct ideas and foibles, but the overall principles remain the same across these. Unsurprisingly, considering that these are within the the GLM, the generalized linear model framework. Obviously, we're kind of all familiar with that modeling approach to these types of problems these days. So this will probably be talked about in future webinars. So if you're interested in this topic, please get in touch and please let me know, and I'll be happy to let either myself or some of my colleagues who be doing future webinars know that we may want to look into this subject in depth in future. So this is just kind of a taste, a preview of what's going to be up in an upcoming release. I just thought it'd be interesting and it kind of fits with the other prediction stuff that we talked about earlier. This kind of area where sample size, the ideas of sample size and prediction are intersecting and kind of finding overlap here in ways that I find interesting. And even though these two areas have kind of maybe up front you may not consider to be natural partners with each other. So to finish up, sample size and prediction, these are important aspects of clinical trials, and there's areas of interaction despite their differing kind of objectives and perspectives. Milestone prediction provides a practical view on when interim analyses, for example, are likely to happen or when the end of the study is likely to happen. Enrollment prediction can help us find when interim analyses are going to happen, for example, if we're looking at mean data or binary data. But if we're looking at survival data, we need to go one level, an additional level, look at event prediction, which builds on the enrollment prediction, builds on having to model stuff like dropout and stuff. Now we're adding in the effect of like the actual survival process itself. So there's a lot of additional modeling needed. And we also saw that there's sample size methods now being developed for the production of clinical prediction models, part of a much wider suite of guidance being put out there to help create more robust clinical prediction models, which have higher probability of actually succeeding in real world clinical scenarios, given how many of them are failing right now, with COVID-19 clinical model prediction models being an obvious failure case, it feels like at the moment. So we're talking about these important model performance criteria and kind of making sure that these reach the thresholds of interest. And just to mention that there are, like we only talked about here about, I suppose, the model performance criteria, like how well we want this model to do. But if we're talking about, like, say, validating the model, there are methods available for that. And as this area expands, I imagine there'll be lots more sample size calculations that look more specifically at things like discrimination versus calibration and stuff like that. But for now, focusing on these kind of model performance criteria and kind of criteria to help us to kind of make it more robust against overfitting and over optimism, and kind of getting one that's probably more representative of one that will actually work in the real world and hasn't just been kind of perfectly tuned to perfectly predict the data we already have back at itself, which isn't a very useful solution. So if you have any questions after this webinar, feel free to get in touch at info@statsols.com. And if you want to try Enquiry, if you don't have access to Enquiry or you don't have access to one of the additional tiers of Enquiry, like adaptive design, feel free to go to statsols.com/trial, where you can try Enquiry for free for 14 days using just your email address, nothing more, and you'll be able to use it within your browser while you're doing that. And as I mentioned, if you want to see previous webinars or previous training or other videos that I've done or my colleagues have done, you can go to statsols.com/start. And just to mention that all the references used for this demonstration are available at the end of this slide deck that will be sent to you after, very briefly after this webinar is complete. So I think we were running a bit over time, so unfortunately I don't think I'm going to have time to take questions, but I've seen your questions. I will be answering them via email later today or at the very latest tomorrow. So I apologize for that, for overrunning a little bit, but hopefully you find some of the concepts and ideas here interesting. It's kind of an interesting kind of merge type of topic here, kind of looking at two different areas, seeing where they overlap, mostly where they overlap. We could look at in future where they differ, but hopefully got something interesting out there, two kind of interesting areas of overlap. So without any further ado, I'd like to thank you so much for attending today. Hopefully you sign up for future webinars, and yeah, hope you have a good day and good afternoon. So thank you so much and goodbye.